people wrote the wrong thing there. So let's go. Number 1. A researcher company compares incomes of people who live in rural areas with incomes of people who live in larger cities. Observational study or experiment? Yeah, definitely. I mean, you're not going to build homes in rural areas and make people live in it just to see what their income is, right? So definitely observational study. Number 2 is the one that's kind of been, I guess, a little bit of disagreement. A doctor studies the increases or decreases in blood pressure of people who are stung by bees. What would you think?
Observational study.
Yeah, I think observational study. A couple people argued that it would be fun to sting people with bees.
I mean, it would be kind of fun, but
maybe. I don't disagree. Especially, the people that I deal with when I go to work every day, it would be kind of fun to see them stung by bees sometimes.
Experiments are not very fun.
Right. What kind of? I mean, it's
not painful ones.
Yeah. So, yeah, that's observational study. It wouldn't be experiment. Number 3, however, so she's going to take this fertilizer and put it in 10 rows of plants and then not in the other 10. That's definitely a what? That's definitely experiment. Okay? Number 4, was this a randomized comparative experiment? Yes or no? No. There's one word, and it's repeated twice. And that's why this is not randomized comparative experiment. What's that word? Volunteers. Right? We said yesterday, if people are volunteering, that creates a what? Creates a bias. It's a non-random type of experiment here. So therefore, I don't know if it's experiment even, but it's non-random. So therefore, it would create a bias, and it cannot be a randomized comparative experiment. So that's a no. Okay? It's got to be random. You can't have people volunteering because that's not random. Next, number 5. You want to know if homes that are close to parks or schools have higher property values than other homes. What do you think? Yeah, definitely observational study. A lot like number 1. Okay, you're not going to build homes. You're not going to go through an experiment where you build homes close to parks and schools, and then some homes that are not close to parks and schools just to see, whether or not they have higher property values. You're just not going to do that. Now, you might take homes that are closer versus homes that are not closer and see, but you're not going to do it. You're not going to control that treatment. Number 6, you want to know if dog food that contains omega-3 fatty acids gives dogs a shiny coat. Experiment or observational study? Yeah, it could be an experiment. Now, somebody probably could say, well, it could be an observational study. You're not wrong. It could be, but it would be okay to do this as an experiment because omega-3 is not going to hurt dogs, right? It's like a supplemental thing. It's going to be good. Number 7, you want to know flowers that are sprayed twice a day with a mist of water stay fresh longer than flowers that are not sprayed. Definitely an experiment, right? And then finally, number 8. Number 8, honestly, there could have been multiple answers. Okay? So what it says is the researcher studied the effects of fiber supplements on heart disease. So he identified 175 people who did take fiber supplements and 175 who did not. And he was able to see that those that took fiber supplements had 19% fewer heart attacks. So they concluded that fiber supplements reduces the incidence of heart attacks. So why might that researcher's conclusion might not be valid? Why would it maybe not be valid? What do you think? What are some things y'all wrote? Maybe they weren't like really regimented on taking those fiber supplements? Maybe. What else? What do you got?
They didn't all have the same diet.
Yeah. Like, for example, what kind of people take fiber supplements? What kind of people take supplements? Maybe. What else? Why else? Maybe their doctor told them to take them because they had underlying issues where fiber might help them. What else? Why else might people take supplements?
They want to be healthy.
Yeah, some people take supplements because they just want to be healthier. Well, if they want to be healthier, what else might they do? They might exercise. They might have a better diet. So if you have someone who's healthier because they're taking supplements, might they do other things that would actually cause them to not have heart attacks? So what I wrote personally is I put people with a healthier lifestyle are generally the ones who take supplements. Now, what you guys wrote, probably really good too, right? Now, well, maybe not, because remember I'm right, you're wrong. No, maybe y'all wrote some good stuff. I didn't even write anything for B. It says, describe how the researcher could have conducted the study differently to produce valid results. Now, I have an overall, like a general thing I think you could have said, but what are some things y'all said for B? Yes. I think you would need to make sure the study included people who had the same age and lifestyle, where some of those were taking fiber supplements and some of them were not. I think that's important. What else? That goes right along with what I would say, what Olivia said. Anybody else?
People who had problems in the past.
Yeah, it could have been someone who had underlying, heart problems in the past. And that's why this would not have worked. And maybe if I could have pinpointed those people and then seen how adding fiber to their, daily supplements maybe would have helped them. Basically, because we could talk about this probably for a while. Basically, if you want to make a better study, you have to try to control as many variables as you can that are the same, except for what? Except for that one, what do we call it? Treatment, right? So that kind of goes along with what Olivia was saying. Like if I could make sure I have people that are maybe the same age bracket, maybe they have the same lifestyle, maybe they have a similar diet, maybe they have similar underlying diseases or not underlying diseases. If I could control all of those variables to the best of my ability, but then have some of them take fiber supplements and some of them not, then maybe I could see the real result of those fiber supplements, whether they're good or not good. You see what I'm saying? You need to have, control over it as much as possible. So there you have it. So yesterday's lesson, Intro to Statistics. There were 5 words that kind of all encompass the idea of statistics. What were they? All of them are important. You have to analyze. What do you have to do before you analyze? You got to collect it, right? You got to collect the data, and then you can analyze the data. Then once you analyze the data, you got to be able to say, hey, what's this data saying? Interpret. That's 3. Then, once I kind of understand what that data is saying, I need to be able to explain it, right? I need to be able to tell people. And kind of along with that explanation, you need to be able to present it, right? In a way where other people see the value of what those statistics are. So, those 5 things. It's not just collecting data, okay? It's not just analyzing data. Statistics include all 5 of those steps. Collect, analyze, interpret, explain, and present. So, we talked about that. The other thing that we talked about, really 2 more things. The other thing we talked about is what's the major difference between experiment and observational study. What's the major difference? In an experiment, I am doing something, right? I am causing the treatment. Now, in an observational study, is there a treatment? Yeah, but I'm not controlling it. It's just happening, and I'm just kind of stepping back and watching to see if it causes some type of change. That's the difference. Experiment, I control it. Observational study, I'm just watching it. Okay? And then the last thing that we talked about that was important that you need to kind of take on with you is randomized comparative experiment. To be a randomized comparative experiment, what has to be key first? Random. Okay? You can't have volunteers. You can't have convenience samples. Remember what convenience was? The first people that you come to, you can't have biased type samples. It has to be random. And then, of course, comparative means they have to be comparing apples to apples, except for what? The one treatment. Okay? That's the key. So, that was yesterday. Feel good about it? All right, we're going to move on into today's lesson. Another easy day. I think you guys will think the same. Dang on. Thing's big. That's one of them like turbo chargers. You could charge everybody's phone in the room with that sucker. Just get you a cord that has a bunch of different outlets on it, and you can just fire on everybody's phone. What do you think, Matthew?
Yeah, probably.
Okay, so have you guys ever been watching TV? And on the TV, yeah, thank you. That's good. Good answer. Good answer. Have y'all ever been watching TV? And on the TV, I don't know, maybe y'all don't watch news very much, but on the TV, all of a sudden it pops up and it says, 82% of all Americans believe that the president's doing a poor job. Y'all ever see something like that? Never? Some type of percentage? 70% of all teenagers, eat Captain Crunch. I don't know. I love Captain Crunch. It's like my favorite cereal. It hurts the roof of my mouth because I eat so much at once. Y'all don't like Captain Crunch?
I like it.
Captain Crunch is amazing.
It's not my first choice.
Well, your first choice is stupid.
Yeah, it's stupid.
Anyways, all right. So listen. So many times you see those percentages, or at least I do, and I'm like, no one ever asked me that question, right? So how are they confident that 82% of all Americans?
I made up a number.
Well, did they? Maybe they didn't. You hope they did it, right? I mean, maybe they're like teachers and they just lie all the time when they're making stuff up, like I do.
I thought you were always right, though.
Well, I am always right. I just lie about being always right, anyways, what just happened? Y'all see that? Oh, y'all didn't see that. What is that? Okay. There was a big ruler that just popped up on my. It's weird. It wasn't even up there. All right. Anyways, I always think to myself, they never asked me that question, and yet they're saying like 82% of all Americans.
I guess you're not the 40%.
I'm not, for sure. They don't care about my opinion, which they should, because why? Because I'm always right. Anyways, here's the point. It is very, very unlikely if I'm doing a survey, no matter what the group is that I'm trying to pinpoint, it's very unlikely that I can reach the entire what? Population. You see, a population, that's the entire group of people, okay? The entire group of people that I'm trying to approach, or I'm trying to access, if you will. Now, if I'm talking about the entire group of people, there are these things that we call parameters. Parameters that we use sometimes to describe a certain data point or a certain summary number about that population. And two really popular ones are average and percentage. Okay? And we have two different concepts here, and we're going to take both of these and we're going to just kind of keep dropping them down. Right now we're talking about population mean. Now, y'all heard the word in math mean before, right? Mean. What is the mean? Not median. Median is the middle number if the numbers are put in order, right? What's mean? It's the average. How do we find average? You add them all up and you divide by how many there were, right? So y'all know how to find mean. If we're talking about the entire population's mean, they call that mu. Okay? Now, is it easy to find mu? No, it's really hard actually. Another data point that's important is what we call the population proportion. Population proportion is kind of like probability. You got to write it as a fraction, right? That first example I gave you guys, it is a population proportion. If I make a statement like 82% of all Americans believe the president is doing a bad job, that is a population proportion. The way you start with that is you have to set up a fraction. And that fraction is favorable over total. Remember we did that with probability? It's very similar. Here's the difference. Once you set that fraction up, you want to change it to a what? Starts with P. Percent. You want to change it to percent. And we'll talk about that in just a second. So for example, something that would be a population mean that we might want to check in on is like the average weight of all middle-aged female Americans. Now again, is that going to be easy information to access? Goodness gracious, no. Okay, there's a lot of middle-aged female Americans, and to think that I could get every single one of them's weight so I could average them all up is it's impossible, right? Now, population proportion might be like the one I told you about a minute ago. What is the proportion of likely American voters approving of the president's job performance? Once again, that's a hard piece of information to access. So, instead of us trying to access the entire population, what do we then focus on? We talked about it yesterday. When I can't get the entire population, I get a what? I get a sample. Because a sample is just a representative group that is drawn from that entire population. Because I can't get the entire population. It's impossible, right? Impossible. So I draw from a sample. Now, when we talk about a sample, we don't call it a parameter anymore. We call it a statistic. And one of our statistics, when we talk about our samples, is our sample mean, which we refer to as X bar. X bar. You know why we call it X bar? It's X with a little bar on top. When we run one of our little things, one of our statistics in our calculator in a minute, we're literally going to find X bar. And guess what X bar represents? That sample's mean, the average, okay? Which you already told me how to find it, right? You add up all those values and you divide by how many there are. And I know the examples that we're going to do, you can do those easily without what I'm going to show you in the calculator, but I'm going to show it to you anyways, because we need that for other things. Then the sample proportion might be what we refer to as P hat, because it's like an italicized P with a little hat on top, P hat. Okay? There's a big difference between those two. To find the sample average, mean, we add them all up, divide by how many there are. To find the sample proportion, we write a what? What'd I tell you? We write a, before the percentage, we write a fraction. We do what over what? Favorable over total. And then, Addie, we turn it into a what? Percentage. Okay? Very simple. In fact, that's the first example that we're going to do. Okay? A local radio station surveyed a sample of their listeners to find their favorite music genre, and they found the following result. Now, we're going to assume a couple things. This radio station is probably the kind of radio station that plays a big genre of music. Here's why. If it were a country music station, who do you think is probably listening to it? People who love country music. So there probably wouldn't be a wide variety of what they prefer. So this is probably one of those random radio stations that plays a little bit of everything. But there's 4 categories that they ask. Country, pop, rock, and R&B. Here's what they want to do. They want to find out what is the estimated population proportion of the most preferred music genre. Okay, guys, look at the data. What is the most preferred music genre? It's rock, right? How do we know it's rock? It's got the most. 52 people voted for that. That's more than 45, 36, and 25. So, we set up a fraction. What do we put on top? Favorable. Favorable is the most preferred, which you just told me was rock. So what do we put on top? 52. And what do we put on the bottom? 158. I don't see 158 anywhere, Eugene. Where'd you come up with that number? That's right. We added them all up. Now listen. Let's say you're listening to this radio station after they've done this survey. Are they going to say 52 out of 158 of our listeners prefer rock and roll? No. They're not going to say that. What are they going to do, Addie? They're going to turn it into a percentage. Population proportions are always turned into a percentage. Okay? How do we turn a fraction into a percentage?
The 158 is 100% and find the percentage of 52.
So how do we do that?
Multiply 52 by 100 and divide 150.
Oh, goodness. That's too hard. Let's do it easier. Grab your calculator and go 52 divided by 158. Go 52 divided by 158. That's going to be way easier for you. What's 52 divided by 158? 0.329. That's a decimal, right? What do we do to change that to a percentage? So you're listening to the radio after they've done this survey. What are they going to say? About 33% of our listeners what? Prefer rock. That's what they'll say. Okay? Because that's how we refer to population proportions. We're not going to say about 52 out of 158 of our listeners. No. They're going to divide that and change it to a percent. Okay? That's population proportion. You set up a what? Fraction. Top number is the favorable. What is it they're looking for? That's the top number over the total. Favorable over total. Population proportion. Real simple. Let's move on to population. Hang on, time out. I keep saying population proportion. Was 158 listeners really their population? No, that was just their what? Here's the point. That's just the sample. But you hope what? You hope that your sample is representative of your population. Okay? That's what you hope. Now, is it likely that it's wrong? Maybe. But that's what you hope. Okay? If I am developing some type of product and I want to sell it to teenagers, so I poll 100 teenagers and 73 out of that 100 tell me that they think that the product that I want them to use would be awesome. What would I do at that point if 73 out of 100 said that my product idea would be great? Brag, that's it? I just brag about it and then be done with it.
Yeah.
What would I do? I would mass produce it. If 73% of my sample size say that this is a good product, wouldn't I want to sell that? Now, what happens if my sample size was wrong?
Well, then you go broke.
Yeah, probably. Here's the point. When we talk about our sample, because that's what we can access, you hope, like Liam said, that it's representative of your population. Okay? You can't do population mean. You can't do population proportion. But you can do sample mean, and you can do sample proportion, and you can hope that it's indicative of what your population proportion and mean would be. Okay? Now, let's look at the next problem. Here we have a sample of students that are in the 10th grade Honors Algebra 2 class, and they were surveyed to determine the number of hours spent studying or doing homework each week. The results of the survey are given below. 5, 10, 7, 6, 11, 4, and 2. And then they ask me, what is the estimated population, what? Mean, based on my sample. Okay, mean. What's mean? Average. So, you're going to grab your calculator more than likely. You're going to go 5 plus 10 plus 7 plus 6 plus 11 plus 4 plus 2. You're going to get that total and divide it by how many there are. And how many are there? 7. So do that real quick and grab. What'd you get? Oh, you added them. You got 45. Now, what's 45 divided by 7? 6.43 is my population mean. Okay, I'm going to go ahead and write that. 6.43. Now, I want to quickly show you guys how to do this in our calculator. Not because that was hard for you. That wasn't hard, I know. But I just want to make sure you understand where to go in your calculator, because the next couple of days, we're actually going to be applying this to find other data. Okay, other data. And it's all done the same way. So grab your calculator out and do what we always love to do. Second plus 7, 1, 2. Reset it. You with me? Okay, so here's what I'm going to do next. I am going to enter data. Well, if I want to put an equation in this calculator, don't I always go to y equals? Okay. If I want to enter data, I always go to stat, edit. Everybody find the button stat, Brady. Everybody find the button stat and click it. And then you see how edit pops up? We're going to go stat, edit. And then guess what we're going to do? We're going to enter our numbers. You got 5, 10, 7, 6, 11, 4, and 2. Okay, stat, edit. That's where you're going to enter data. But now we want to run a statistics analysis, if you will. So here's where we go. You go back to stat. You've entered your data, go back to stat, but this time scroll over to calculate. And we're going to do a one variable statistics. We just had one variable. We have one thing, right? The hours they spent studying and doing homework. We push enter, enter, enter. And sure enough, right there at the very top, what do you see on the far left side? X bar. What does X bar stand for? Your sample, the numbers we just entered, mean, average. It's 6 point what? Isn't that what y'all told me when y'all did it the other way? Now, there's some other numbers here that we're going to talk about later. So you need to know how to run this. Stat, edit, enter your data, stat, calculate. You run a one variable statistics test. So we got 6.43. All right, so look, my estimated population mean is 6.43. Now, how much confidence would I have saying, you know what, this little sample of 7 people has to be extremely indicative of all of my honor students? So I'm really confident that the average number of hours that my honor students spend studying and doing homework every week is 6.43. Are you confident of that? No. Sometimes when it goes to taking your mean and applying it from a sample to a population, we like to give ourselves just a little bit of a window. Okay? That little window that we can be more confident in is called our margin of error. A margin of error is loosely defined as the largest expected size of the difference between the estimate and the actual population value that is being estimated. Blah, blah, blah. Right? Here's what that means. Let's say I have a sample, and I get an average, like this example right here, and the average weight was 45 pounds. But I want to apply that to a population. And I don't feel comfortable saying that the population is exactly 45. I want to give it a margin of error of 2 pounds. I can then confidently say, you know what? I bet my average actually lies between what? Huh? Not 2 and 45. Not 44 and 46. It's 43 to 47 pounds. What did I just do, y'all? I subtracted the margin of error from the average, and I added the margin of error to my average. That allowed me to say, hey, I know my sample mean was 45, but if I want to compare that to my population mean, I need a little wiggle room. So that margin of error is subtracted from and added to my average to give me that window that I feel really confident my population mean would fit inside. Does that make sense? So that's what margin of error is. It's not a big deal. We simply add it and subtract it from our average. Okay? So we have our last problem here. Researchers have questioned whether the traditional value of 98.6 is correct for a typical body temperature for healthy adults. Suppose that I plan to estimate mean body temperature by recording the temperatures of the people in a random sample of 10 healthy adults and calculating the sample mean. All right, so sample mean means I do what with these values? We add them all up, and I divide by how many there are. Now, I'm going to go back to my calculator and use stat edit. Will y'all listen to me just for a second if you've kind of tuned me out? If you're ever in your calculator and you want to delete all of those values at once, you can go up to your list and please don't push delete. It'll actually delete L1, and you actually have to you can't just second plus 712 to get it back on. You have to do a little bit different. So anyhow, what I want you to do is go up there and push clear enter, and then it'll clear that list, but it won't delete it. Clear enter. Don't push delete. Push clear enter. Now, here we go. Let's enter all these numbers. 97.73. Enter. 98.76. Enter. 98.27. Enter. 99.95. Enter. 98.47. Enter. 98.49. Enter. 98.97. Enter. 98.68. Enter. 99.27. Enter. And 99.25. And I think I entered everything correctly. But remind me, how am I going to run a test to find out my X bar, my mean? Go back to stat. This time scroll over to calculate and run a one variable statistics. Push enter a bunch. And what was my mean temperature from this sample? 98.78. And I'm gonna do exactly what Landon just did. Look at my answers. All of them had how many decimals? All of them had 2. That's why I'm gonna leave this as 2. So it matches. Okay? If you wanted to put the 4.784, that's fine. But I want this to kind of match. Now, last thing. They give me a margin of error because they want me to apply this to a population. Well, I don't feel 100% comfortable saying 98.78, but I do feel 100% comfortable giving it a margin of error. What do I do with that margin of error, 0.38? You subtract it and you add it to your mean. So 98.78 minus 0.38, what'd you get? 98.4 degrees. And then 98.78 plus 0.38, what do you get? 99.16. Now, I would feel really confident saying that my population mean would lie from 98.4 to 99.16. So here's my question. Can we feel confident that 98.6 degrees Fahrenheit is still a good number to use for average body temperature for healthy adults? Sure. Why? Because it fits in my window, doesn't it? If it fits in my window, then we can say we feel comfortable about it. All right, so what do you think? Easy, right? Easier than less? Okay, so I'm going to give you your worksheet, and I want you to do all of them. Okay, that's 9 problems. Here it comes.